Okay, so what do we do now that we recognize it's in quadratic form? Now what? Okay, so the steps are as follows. First thing is we want to identify the equation as quadratic form. In other words, jump through all those hoops that we just went through just to make sure that, okay, yeah, it does follow those 5 characteristics. And then set the equation equal to 0. Then we're going to let some variable u, which is why we call it a u substitution, be equal to the original equation's linear or middle term. And this is something that we're going to write down because we're going to eventually use that to solve the problem. Step 3, we want to find the square of the new variable. So in other words, once we figured out what u is, let's figure out what u squared looks like. And if done right, we should see 2 of those expressions show up in the actual problem. So our step 4 is to substitute the new variable u into the equation to get a quadratic equation and solve for the new variable u. So we're going to rewrite the problem in terms of u. We're going to solve u because now it's going to look like something we know how to solve. But then we're not done because it's not about solving for u. It's about solving for x or solving for whatever variable we're given. So that brings us to step 5. So to solve for the original variable, we're going to substitute the equation from step 2 into the solution that we found. So we'll solve for u, we'll get a number. I want to take the original thing that I substituted for and set that equal to the number we found. And then number 6 is we want to check our solution. It's always a good idea to double check that it does work because if one of our expressions involves a fractional exponent, that does mess with the rules a little bit. So if your equation includes fractional exponents, you definitely want to go back and check that you're not violating some other rule. Alright, so let's take a look at this first equation, x squared minus 8x squared minus 9. Double check it fits all the characteristics, so equals 0, last term is constant. They both have x's in them. The exponent of the first term is double the exponent of the middle, so it definitely fits what we would consider to be a u substitution. So I'm going to look at the middle or linear term, and that x squared is what I'm going to replace with u. And then I want to ask myself, if u is x squared, what would u squared look like? Well, that would be x squared squared, and using our exponent rules, that's x to the 4th. Okay, so what is that in the terms of the original equation? Well, that x to the 4th now becomes u to the 4th minus 8u, u to the 4th, u squared minus 8u minus 9. And now that looks like something we know how to handle. So I'm going to try to factor it. It's got to be u, and I need factors of 9 that give me an 8. Well, how about a minus 9 and a positive 1? That seems to work, right? Then I want to set each factor equal to 0. U plus 1 equals 0. And I get that u is equal to negative 1 and positive 9. Now, before I get all excited, we got to realize that I want x, not u. So I'm going to take x and set it equal to each one. So x squared equals negative 1, and x squared equals 9. And then solve. So to solve for x in this case, I want to take the square root of both sides. So that gives me x equals plus or minus I, and x equals plus or minus 3. So we actually get 4 solutions. Only 2 of them are real, so please be careful with directions. And if it only wants you to identify the real solutions, then we would only have plus or minus 3 in this case. Okay, so in this next example, I want to just confirm mentally to ourselves that we're dealing with something in a quadratic form. So it is equals 0, last number is a constant. If I look at the middle variables, they're both the same. And the first exponent is double the second exponent, so we're fitting in that pattern. In which case, I want to set u equal to the linear variable. So u is going to equal x to the 1/3. And then I want to ask myself, what would u squared look like? Well, if I take x to the 1/3 and I square it, I get x to the 2/3. Okay, so then I want to go back in and replace the x's with the u's. So I get 5u squared plus 11u plus 2. And now I want to try to factor this. Okay, so 5u squared, well, that's got to be 5u and u. And there's got to be a 2, it's got to be 2 and 1. And since I want an 11, then I want to make sure that I multiply the 5 and the 2 together. So we'll do that. And everything is plus. And so then I want to solve for u. So we get, sorry, I'm going to scroll down here. So we get 5u plus 1 equals 0, and u plus 2 equals 0. So then I want to move over those expressions. So I get 5u equals -1, and I get u equals -2. So then u would be -1/5 and -2. Okay, so my goal, however, was not to solve for u, but to solve for x. So I want to write down that those two numbers that I just found are actually solutions in terms of u instead of x. So x to the 1/3 equals -1/5, and x to the 1/3 equals -2. And then, how does one get rid of a third as an exponent? Well, if you want to figure out what x is, then you want to go ahead and cube both sides. So I end up with x equals 1/5 cubed would be -1/25, and -2 cubed gives us -8. All right, this last example, we again go through the thought process. We see that it's set equal to 0, last term is constant. The middle term, yeah, it's definitely in quadratic form. So what would u be this time? Well, we're going to let u equal x plus 3. And so what would u squared look like? Well, that would just equal u plus 3 squared. So when I do my substitution then, I get u squared plus 7u minus 18 equals 0. Okay, so now I want to try to factor that. Well, obviously u squared is u and u. Then I need two factors. I need factors of -18 that'll end up giving me a 7. Well, but 9 and 2, because 9 and 2, I can see a 7 out of that. So I want the 9 to be positive and the 2 to be negative. And then I want to set each of those equal to 0 and solve, and hopefully you'll recognize we get 2 and -9. And then I want to go back in and replace the x plus 3 and actually figure out what x is, not just what u is. Okay, so we said that x plus 3 equals 2, and x plus 3 equals -9. So when I work that out, I get that x is, so you subtract 3, So negative 1 for that one, and then when I subtract 3 here, I get negative 12. Okay, so the last topic, I guess, in this miscellaneous section deals with radical equations. So what exactly is a radical equation? Well, a radical equation is an equation where a square root, cubed root, or any other higher root happens to be there. Basically, an equation with a square root in it. Makes it radical. So an example of this is x cubed equals 9, and this actually is a good illustration of what we got to be careful with here. So if I want to solve for x, how do I get rid of the square root? Well, that means I'm going to have to square it. And so I end up with x equals 81. Okay. Now, because we end up squaring things, you got to realize that sometimes negative numbers are going to creep in here, because sometimes if I square something that's already positive to begin with, a negative sort of gets hidden around. So with dealing with radical equations, we always want to get in the habit of checking our solution to make sure that it actually works in the original problem. So is it true then that the square root of 81 is 9? Yeah, that's actually a true statement. But sometimes we'll get what's called extraneous solutions to show up. Okay, so in general, what we want to do is we want to rearrange our terms so that a radical is on one side of the equal sign. Then we want to square both sides, which thus eliminates one of the square root, and then solve. Now, if we square both sides and that does not eliminate the square root, we repeat the process. So we isolate the radical on one side, get everything else on the other, square it, and see what we get. Okay, and then one thing that's going to help this go a little bit quicker is if we understand I guess a foiling pattern. So if I take a plus b squared, that's a plus b times a plus b, which is a squared plus ab plus ab plus b squared, which if we combine like terms, that's a squared plus 2ab plus b squared. Okay, so this actually has a name called the perfect square trinomial, but it's a very powerful shortcut if we understand how to go from the initial step to the last step. So if we recognize that that's the pattern, because what are we actually doing? I'm squaring the first, doubling the product of the two terms, and then squaring the last. So if I can recognize that typically goes a little bit quicker for us. Okay, so let's look at some of these radical here. Alright, so square root of 2x minus 1 plus 2 equals x. So first job, get the 2 on the other side. So that's x minus 2. And then I want to square both sides. Well, on the left side, I'm left with 2x minus 1. On the right side, here's where that foiling pattern will save us a little bit of effort. I should get square the first, double the product, so x times negative 2 is negative 2x. Double that, we get negative 4x, plus the square, so plus 4. Okay, so then from here, we know lots of stuff about quadratics. Clearly, I want to get the 2x minus 1 to the other side. So I'm going to subtract off 2x. I'm going to add 1. And we get x squared minus 6x plus 5. Okay, so then we try to use our solving techniques. And I think factoring is perfectly fine for this one. So let's see. We get x minus 5 and x minus 1. So we get two solutions of 5 and 1. Okay, so this is where I mean we want to come back and check that we didn't accidentally bring in an extra solution that's not really there. So let me set up a check step here. So I want to check that when I plug in my two solutions that they actually work. Alright, so the square root of 2 times 5 minus 1 plus 2, does that actually equal 5? Well, let's see. The square root of 2, so 2 times 5 is 10. 10 minus 1 is 9. So I end up with 3 plus 2 equals 5. So the 5 checks. What about the 1? Well, square root of 2 times 1 minus 1 plus 2, does that actually equal 1? Well, 2 times 1 is 2 minus 1, so we get 1 here plus 2 does not in fact equal 1, so that does not work out. Now, just as a personal note, I actually appreciate it when a student will circle that answer and give that to me on a test. And the reason why I appreciate that is I can see that they checked the 5 and I can see they checked the 1 and the 1 did not work. So I can see that they actually went through and did all the steps. Whereas the student that just says, oh, I got 5, I don't know if he, I mean, I hope he did it right. But anyways, so, but yes, the answer would just be 5. But I do prefer to see that you actually checked it and recognize that it's not a correct solution. Okay, so in this one, a little more complicated. So just take a deep breath before I even get started. With two radicals, I already know that I'm going to have to square twice. So I'm going to have to do a lot of multiplying before I can finally get rid of the square root and get to a point where I can solve something. So let me start by, let's move over that square root of x plus 4. So I get square root of 3x plus 1 equals 1 plus the square root of x plus 4. Now, when I square both sides, on the left, I get 3x plus 1. That's not that bad. But on the right, this is where I'm going to take advantage of our pattern. Okay, pattern said square the first. It said double the product. And it said square the last. Okay, so from here, I can see there's a good portion of simplifying that I can do. So that's 1 plus 2 square root of x plus 4 plus x plus 4. Okay, and let's bring everything over. So we'll subtract 1, subtract x, subtract 4. Let's see, so this would be minus x minus 1 minus 4 over on that side. So I get 2x minus what? Minus 4 equals 2 square root of x plus 4. And both things are even, so to me it makes sense just to divide everything by 2. So I get x minus 2 equals the square root of x plus 4. And now you can kind of see why I said it's going to take us a little while because we got a few more steps here. So from here, we're going to square again. So that's square the first, double the product, plus the square of the last was x plus 4. And we're going to subtract x off. We're going to subtract 4 off. So we're left with x squared minus 5x equals 0. Let's see, GCF that. So I can take x out, so that's x minus 5 equals 0. So what does x in this case equal? That equals 0 and 5. Okay, now before I get excited, I want to go back and grab the original problem. And just double check that it does actually work in both. So it was 3x plus 1 minus x plus 4 equals 1. Okay, and we said that the answers were 0 and 5. Okay, so let's try a 0. See if that works. So if I plug a 0 in, that's just going to be 3 times 0 plus 1. So that's just 1 minus the square root of 4 equals 1. Or it's not going to work. I can already see the problem. So here we get 1 minus 2, which does not equal that, because it's actually negative 1 on one side, so 0 doesn't work. Alright, what about 5? Is 5 going to work out for us? So 3 times 5 plus 1 minus 5 plus 4 equals 1. Okay, so we get 3 times 5 plus 1, so that's square root of 16 minus square root of 9 equals 1. And the square root of 16 happens to be 4 minus 3 equals 1, so we do get 1 equals 1. So 0 does not work, 5 does. So just be patient with these radicals. It's really easy for a sign mistake to creep in, and all of a sudden we've made a silly error that we didn't necessarily have to. So anyways, good luck.